This is 9.1, section 9.1, significance tests, the basics of significance tests. So here's a couple questions. Do teens prefer texting over face-to-face communication? Here's a different scenario. The National Association of Colleges and Employers stated that the average starting salary for students graduating with a bachelor's degree in 2017 was $50,516. Is this true at your college? So what we'll be doing in this unit is using data from a sample to test if a particular claim is true. And this is called a significance test. So a significance test is a formal procedure for comparing observed data with a claim, also called a hypothesis, whose truth we want to assess. The claim is a statement about a parameter, like the population proportion, p, or the population mean, mu. A significance test starts with a careful statement of the claims we want to compare. And so the claim we weigh evidence against in a statistical test is called the null hypothesis. We abbreviate it H sub 0, and usually we just say H naught. Often the null hypothesis is a statement of no difference. The claim about the population we're trying to find evidence for is called the alternative hypothesis, and we abbreviate that H sub A. So let's look at this example again. The National Association of Colleges and Employers stated that the average starting salary for students graduating with a bachelor's degree in 2017 is $50,516. Is this true at your college? So suppose a simple random sample is taken of 30 students at your college that graduated in 2017 with a bachelor's degree, and the average starting salary for the sample was $45,000. So there could be two possible things going on here. The first one is that the true mean for your college is 50,516. It's no different than what the National Association of Colleges and Employers is stating is the mean for all colleges. So it's just no different at your college. The sample mean that you got, the 45,000, just occurred by random chance. Nothing unusual is happening here. Here's another explanation. The true mean at your college could really be something other than 50,516, and that's why you got a sample mean that was different than 50,516. So in this situation, the null hypothesis would be that the mean, the true mean, is 50,516, and that's the claim you're trying to see if you have evidence against. And the alternative hypothesis is that the true mean is something other than 50,516. In any significance test, the null hypothesis has the following form. You'd say the parameter equals some value. So it's always equals. You always use the equal sign in a null hypothesis. The alternative hypothesis has one of the following forms. You only write one of these. Either the parameter is less than some value, the parameter is greater than the value, or the parameter does not equal that value. And to determine the correct form, it just depends on the question, so you have to read the problem carefully and look at the context of the problem. All right, let's look at another example. The credit card industry asserts that no more than 50% of college students carry a credit card balance from month to month. In an SRS of 310 college students nationwide, 217 carried a balance each month. Does this sample refute the industry claim? In other words, do we have evidence by taking the sample that the percent of college students who carry a credit card balance is more than 50%? Because the credit card industry is stating that it's no more than 50%. So our null hypothesis for this situation would be P equals 0.5. We always use the equal sign for the null hypothesis. And the alternative hypothesis is that the proportion, P, is greater than 0.5. And we always want to state what our parameter represents, what our P represents. So P is the true proportion of college students that carry a credit card balance from month to month. The reason we're saying greater than 0.5 in the alternative is that the credit card industry is saying no more than 50%. So we're seeing if we have evidence against that. And so we're seeing if we have evidence that it is actually greater than 50%. Here's another example. The average recovery time for a certain knee surgery is 8 weeks. A group of doctors want to know if the recovery time is shorter when a different surgery procedure is used. So our null hypothesis would be that the mean recovery time, mu, is what we're referring to, so we're going to use mu, equals 8 weeks. The alternative hypothesis is what we're trying to see if we have evidence for, and that's that the mean is, so mu, is less than 8. It says the doctors want to know if the recovery time is shorter when a different surgery procedure is used. So that's why we're using less than 8. And we want to state what the parameter represents. So mu is the true mean recovery time for the new surgery procedure. So another example, you suspect that a certain coin is not fair and is more likely to land on heads than tails. So maybe someone's flipping a coin, they keep getting heads, and you're doubting that it's a fair coin. So you flip the coin 100 times, and it landed on heads 65 times. So is this enough? Basically, you got 65%. When you would expect a fair coin to be 50% heads, you got 65%. So do you have enough evidence to not believe that the coin is really fair? So our null hypothesis would be P is 0.5. It's just a fair coin and just equals 0.5. The proportion of heads is 0.5. The alternative would be P is greater than 0.5 because you're seeing if you have evidence that it's more likely to land on heads. And we want to make sure we define what P is, the true proportion the coin will land on heads. So this is how you would begin the test. You would just state the hypotheses. And then what you want to do to conclude the test is find the probability if the null hypothesis was true. So in this case, if the coin really was fair, what are the chances? What's the probability of getting 65%, getting 65 heads out of 100? Is that, maybe that's very likely. Maybe if the coin was fair, there's just a really high chance of getting 65 out of 100 and nothing really unusual is going on. Or maybe if the coin was fair, maybe it's really unlikely to get 65 out of 100. And in that case, we would have evidence against the coin being fair. So this probability that we try to find is called the p-value. So the null hypothesis states the claim that we're seeking evidence against. The probability that measures the strength of the evidence, that tells us how strong our evidence is called against the null hypothesis, is called a p-value. So this is a definition for p-value. The probability, computed assuming that the null hypothesis is true, that the statistic would take a value as extreme as or more extreme than the one actually observed, is called the p-value. Small p-values are evidence against the null hypothesis, and right now we're just going to look at different values for p-values. We'll talk about how to compute the actual p-value later, but the smaller the p-value, that means you have evidence against the null hypothesis because they say that the observed result is unlikely to occur if H naught was actually true. Large p-values give evidence against give convincing evidence against the null hypothesis because they say, large p-values fail to give convincing evidence against the null hypothesis because they say that the observed result is likely to occur by chance when the null hypothesis is true. So a larger p-value, you do not have convincing evidence against the null hypothesis. The final step in performing a significance test is to draw a conclusion about the competing claims you are testing. So we want to make one of two decisions based on the strength of the evidence against the null hypothesis and in favor of the alternative hypothesis. So you're either going to reject the null hypothesis or you're going to fail to reject the null hypothesis. So basically, if your p-value is small, you reject the null hypothesis, and that means you have convincing evidence for the alternative hypothesis. If your p-value is large, you fail to reject the null hypothesis, and you do not have convincing evidence for the alternative hypothesis. We're going to look at an example. A basketball player is claiming he makes 80% of the free throws that he attempts. We think he might be exaggerating. Here's our null hypothesis, that P is 80%, that he's telling the truth. The alternative is that it's less than 80%. If we think he's exaggerating, then that means we think that the true proportion, the true percent of free throws that he attempts is less than 80%. He's not telling the truth. So P is the true proportion of free throws that the basketball player makes. Always define the parameter when you're stating hypotheses. So we want to test this claim. We're going to ask him to shoot some free throws. He ends up making 64% of his free throws. That is less than 80%. But is it enough evidence to not believe him? Do we have enough evidence to reject his claim, reject the null hypothesis that it's 80%? So assuming his claim is true, and he really does make 80% of his free throws, we calculate that the probability of him making 64% of his free throws is 0.0075, so 0.75%. This is called the p-value. Later we'll learn how to find this calculation. Right now we're just going with that. That's the calculation for the p-value. The p-value is so small, we have very strong evidence against the null hypothesis. So remember, a small p-value, you can reject the null hypothesis. We have convincing evidence that the basketball player makes fewer than 80% of his free throws. Basically, if he really did make 80%, there's such a small chance that he would have just made 64% of his free throws in that sample that we have enough evidence to reject his claim. How do we know when a p-value is small? So it's easy to say it's small, but how small is small? So before we perform the actual test, we set a fixed value that we can compare the p-value to. And we call this the significance level. We write this as the letter alpha, so it's a Greek letter alpha. If the p-value is smaller than alpha, we say that the data are statistically significant at level alpha. In that case, we reject the null hypothesis and conclude that there is convincing evidence in favor of the alternative hypothesis. Last example, for his second semester project in AP Stats, Zenon decided to investigate whether students at his school prefer name brand potato chips to generic potato chips. He randomly selected 50 students and had each student try both types of chips in random order. Overall, 32 of the 50, so 64%, of students preferred the name brand chips. Zenon performed a significance test using the hypotheses. The null hypothesis is p equals 0.5, and the alternative would be that it's greater than 0.5. That's because Zenon says he wants to investigate whether students at his school prefer name brand potato chips, so that the proportion, in fact we're going to define it right now, p is the true proportion of students at his school who prefer name brand potato chips. Let's say he calculates the p-value and we get a p-value of 0.0239. What conclusion would you make at each of the following significance levels? So before we can make a conclusion, we want to decide which significance level to use, and this ideally would be set before you calculate the p-value when you first start the test. So if the significance level was alpha equals 0.05, or what if the significance level was 0.01? So the resulting p-value was 0.0239. What we would do is compare the p-value to alpha. If it's less than alpha, that means it's small enough and we would reject the null hypothesis. So let's look at A. The p-value of 0.0239 is less than alpha of 0.05, so we reject the null hypothesis. That means we have convincing evidence that students at Zenon's school prefer name brand chips. Let's look at B. The p-value of 0.0239 is greater than alpha of 0.01, so we fail to reject the null hypothesis. There is not convincing evidence that students at Zenon's school prefer name brand chips. There's the hypotheses again, just so we can see them.